Hello and welcome to the next part of this video series. In the last video, we successfully proved that 1 plus 1 over n to the power n is less than or equal to 3 minus 1 over n, which is indeed less than 3 for all n greater or equal to 1 and in the natural numbers. So, at the end of the last video, I said that in the next video, which is this video, we are going to prove that the sequence 1 plus 1 over n to the power n is monotonic increasing. Now, we've successfully shown that the sequence is bounded above by 3. It's bounded above by 3 for, in fact, all n in natural numbers, including n equals 0, which you can check. And it's also bounded above by 3 minus 1 over n, which is a variable expression for all n is greater or equal to 1. But we're just going to leave it at 3. So we know now that this expression is indeed always less than 3. Okay? It's always less than 3. So it's bounded above. So we know by the least upper bound property, which we proved in a previous video in this series, some previous video in the series, I think it was either the first or second video, we proved that if a set S, or rather, if a sequence S, Sn, is bounded above and monotonic increasing, then Sn converges. In other words, the limit as n approaches infinity of Sn exists, and it's actually equal to the least upper bound of Sn. So this is a statement that we proved successfully in a previous video of this series. So we have shown that this sequence is indeed bounded above by the number 3. Now all that's left to show is that the sequence is monotonic increasing. For if we show that the sequence is monotonic increasing and bounded above, we can just apply that statement, which is actually called a monotone convergence theorem. We can just apply it, and it proves that the sequence must converge, or in other words, that the limit as n approaches infinity of the sequence exists, and that Euler's number, or E, exists, because Euler's number is literally just defined as the limit of this sequence. So that's our aim today. That's what we're going to show. So how do we do that? First of all, let's take a look at S of n, so the nth term of this sequence. Okay, the nth term of this sequence is just 1 plus 1 over n to the power n. And the next term, the n plus 1th term, is equal to 1 plus 1 over n plus 1 to the power n plus 1. So we want to show that S sub n plus 1 is greater or equal to S sub n, which proves that the sequence is monotonic increasing. So how do we do that? Well, we can expand both of these out using the binomial theorem. The first one is I equals 1 to n of n choose I, multiplied by 1 over n to the power k, and S of n plus 1 is the sum from I equals 1 to n plus 1 of n plus 1 choose I, 1 over n plus 1 to the power I. Now, it suffices to show that each individual term of Sn is less than or equal to each individual term of Sn plus 1 up to the nth term, because S sub n only has n terms. So if we show that each of S of n's term is less than a term of S of n plus 1, we'll actually show that it's less than the corresponding term of S of n plus 1, then S of n is certainly less than or equal to S of n plus 1, because S of n plus 1 has n terms plus an additional term. Okay, so hopefully that makes sense. So we want to show that each individual term of S of n is less than or equal to the corresponding term of S of n plus 1. So we can do that if we show that n plus 1 choose I multiplied by 1 over n plus 1 to the power I divided by n choose I times 1 over n to the power I. I've just realized I've accidentally written a k over here, so I'll just rub that out. Write an I. We can do that if we show that this quotient is greater or equal to 1. Because if this quotient is greater or equal to 1, it's clear that n plus 1 choose I multiplied by 1 over n plus 1 to the power I is greater or equal to n choose I 1 over n to the power I. And so we can then conclude that the summations from I equals 0 to n of both sides, we can do that. We can sum both sides from I equals 0 to n, and we get essentially what we desire. We get that this is true, which obviously means that S of n plus 1 is greater or equal to S of n. So, alright, so this is what we want to do in this video. We don't have much time left, so I'm going to speed up a bit. Okay, so just open a new page. So we were looking at this expression, n plus 1 choose I, 1 over n plus 1 to the power I divided by n choose I, 1 over n to the I. Alright, now using just some algebra, we can manipulate this and change how it looks. And this is actually quite a critical step. So what we do is we're going to completely change how this looks. The numerator is going to look like this now. It's going to be n plus 1 times n times n minus k minus 2 divided by k factorial. And in the denominator we'll have n plus 1 times n plus 1 times n plus 1 I times, so this is I times. And this whole expression here is actually just the numerator, okay? You can verify that for yourself if you want. It's just a matter of expanding out the factorials. Now we're going to also manipulate the denominator and make it look like something which we can work with. Interestingly, this step is pretty critical, even though it's just an algebraic manipulation. It's actually quite an important step, because it's pretty difficult to prove that the sequence is monotone increasing without this step. It's actually quite a crucial step. So this is the expression for the denominator, and this is the expression for the numerator. Sorry, and I've just realized that I've forgotten something. So there's ni times in this expression as well. So I times. And what we're going to do is we're going to divide this stuff. So I'm going to label this stuff in red. We're going to divide the stuff in red by the stuff in green. And we're going to show that that's always greater or equal to 1. Okay? I'm going to show that. So this is pretty messy. I'll open up another page. And so when we divide, remember, we're just going to multiply the stuff in red by the reciprocal of the stuff in green. So it's just going to be, it's just going to be red multiplied by 1 over green. Okay, hopefully that makes sense. So, whoops. Okay, so how does that look like? How does that look like? So that looks like this basically. When we end up actually dividing everything, we can pair stuff up and it'll look something like this. So I'm just going to pair everything up. We get n into n into n minus k minus 2 into n divided by n plus 1 into n into n minus 1 to n plus 1 all the way to n minus k minus 1 into n plus 1. And we have k terms in the numerator and k terms in the denominator. So all I've done is I've multiplied red by the inverse of green, and I've put everything together. I've joined everything up together. So you can verify that for yourself. You can just pause the video and see that that algebra checks out, and it's fine. And now we're just going to compare each sort of cell. We're just going to look at this part, and then we're going to look at this part, and so on and so forth. And we discover something interesting. The first term, well, that's just 1. That's equal to 1. This term can be reduced to n squared divided by n squared minus 1, which is obviously greater or equal to 1 because the numerator is 1 unit greater than the denominator. So that's greater or equal to 1. And we can go all the way to the kth cell, and we see that this is also true. N squared minus k minus 2n divided by n squared plus n minus k minus 1n minus k minus 1. And if we just do some algebra, n squared minus nk plus 2n divided by n squared plus n minus kn minus n minus k plus 1, and doing, whoops, alright, and rearranging this further, it's n squared minus nk plus 2n divided by n squared minus kn minus k minus 1. And so we see that in this case the numerator is definitely greater than the denominator for sure. And you can do this with each individual cell, and because all of these expressions are greater or equal to 1, this entire expression is greater or equal to 1. And that's what we wanted to show. So we've successfully shown that that our series, that our sequence is a monotonic increasing sequence. So 1 plus 1 over n to the power n is monotone increasing. It's monotone increasing, and it converges to a number that is less than 3. Okay? Because we know that these bounds still apply. And we also know that this is obviously greater, it converges to something greater than 2 as well. And you can whittle down your bounds. You can get better and better bounds by simply plugging in numbers here. So for example, 3 minus a half, right, is 2.5. So after, for all n is greater or equal to 2, the sequence is definitely less than or equal to 2.5. And then for n is greater or equal to 3, it's less than 3 minus a third, which is greater than 2.5. And for n is greater or equal to 4, it's less than 3 minus 0.25, which is 2.75. And these you can better your bounds for e basically using this sort of method. And so e does converge to e is a number because e is the limit as n approaches infinity of this sequence. So e is definitely greater than 2, less than 3. So we've established the existence of e, and we've even proved that it has some nice bounds. Thanks for watching.